I'm a second-year medical student. Assalamu alaikum. My name is Aghiad Alkhachem. I'm a second-year medical student, and I'll be here to help you get an intro to pulmonary physiology and better understand lung volumes. Before we begin, let's set the ground rules as usual. If you have any questions, please don't hesitate to ask in the chat. We have checkpoints for you to ask as well, for you to unmute and ask me as quickly as you can. All right, and please, if you don't understand anything, stop me, okay? We're here to learn. There's no fear should be involved. All right, so Bismillah. What's the function of the respiratory system, okay? So basically, it can be narrowed down to two components, ventilation and respiration, okay? So as you can read here, ventilation is the voluntary action of breathing in air, okay? While respiration is the involuntary exchange of gases between the capillaries, alveoli, and tissues of the body, okay? So they're different. Don't use them interchangeably because they mean different stuff. So in other words, ventilation is the first step of respiration, right? You guys know what ventilation means. Every room has a ventilation system, okay? Air comes in. So that's the function of the ventilation system of the body, okay? While respiration, okay, is a delivery of oxygen, the main component of ATP production, just vital for the body, right, to the cells. So the process of delivering oxygen, right, to the cells is called respiration, okay? While ventilation is just delivering the air that contains oxygen, okay? So again, in other words, ventilation is the first step of respiration. It delivers the oxygen needed for tissues. It also expels the metabolic waste, carbon dioxide being the main one, produced by the tissues, right? The tissues have done their metabolic needs and they want to get rid of the metabolites such as CO2, right? And how do you do that? By the ventilation system. Okay, so basically it's just the movement of air in and out, okay? I hope that is clear. If it's not, please stop me. Again, how does it do that? Well, the lungs receive the air, they receive the oxygen, okay, and it travels to the alveoli. And by diffusion, the oxygen goes from the alveoli to the capillaries. You know, the capillaries right here, okay? Oxygen just diffuses through them, right? So that it can be circulated back to the body, okay? And it goes to tissues, and then back to the capillaries where the CO2 will be diffused. Okay, it's a simple system, it's a cycle, right? You bring in oxygen, right? And you get rid of CO2, okay? So ventilation is bringing in the air. Respiration is delivering that the oxygen to our tissue, okay? And then it goes to the cells of our tissues through diffusion. Simple, very simple, just definition. So I hope that is clear. If it's not, please stop me. Again, is it clear? Please say yes.
Yes, it's clear.
Yes.
All right, perfect. I want you guys to be interactive, okay? Don't be sleepy on me. Okay. So this is just basically the membrane, the diffusion, the alveolar capillary membrane. As you can see, this is an erythrocyte. This is how small and tiny the membrane is. You see how just slim it is, right? It just shows you it's very, very capable of diffusion, right? And this is an electron micrograph, okay? So it's not just any microscopic picture, right? This shows you the alveolar membrane and the erythrocyte. You can imagine oxygen coming in, right? And then the erythrocyte being on the surface where oxygen can be easily diffused. All right. So this is just a histological slide. Very clear. Again, so the respiratory system is divided into two. Okay, upper and lower respiratory tract. Okay, the upper ones, right? The upper respiratory tract, the lining of the upper respiratory tract receives large amount of blood flow, right? And it is coated with mucus. And that is for, right, certain functions, including warming and moistening the air before it flows into the lower respiratory tract. But you don't want very cold air. I mean, I never wondered how when you go outside, it's very, very cold, but still you can manage, to receive that air and doesn't really feel cold inside because it warms it up. It's very important. Okay. And that the upper respiratory tract includes the nose, pharynx, and larynx. Okay, as you can see here, air goes in either from here or from the oral cavity, and then towards the larynx, and then to the trachea, right, where we get to the lower respiratory tract. Okay, and that includes the trachea, bronchi, bronchioles. These divisions you'll know more about in later subjects in anatomy, histology, right? But we'll give you an overview of them so you can better understand the physiological functions of the body and the respiratory system. Okay, and then the smallest being the alveoli. Okay, so again, upper, nose, pharynx, larynx, function is to moisten, warm the air up. Okay, and then lower is to receive that air. Right, it also warms the oxygen, obviously, and the air. It warms it up and has many functions. Myriad of functions we're going to talk about and discuss later. Right, so this is just a basic, simple division, okay, of the respiratory system. Okay, so is that clear?
Yes.
Perfect. طيب. So the lower respiratory system, okay, the tracts, the lower respiratory tract. As you guys know, the trachea, you guys took the trachea. Sorry?
Yes.
Come again, please, I couldn't hear you. You can type it in the chat, your voice is a bit laggy. If you have a question, please type it in the chat. We'll have checkpoints, by then try to figure out the mic situation so we can freely discuss it. But for now, we're going to discuss the lower respiratory tract. Okay, as you guys know, the trachea, right, and divides into bronchi. That's the first division. Keep it in mind. That's the first division, right? And then further divides, keeps on dividing, right? And so as you can see here, the conducting zone is also called the dead space. The tissue is not dead. It's physiological dead space. Not really physiological. We get into the detail, right? But when speaking of function, it's called the dead space because there's no gas exchange. Okay, so anatomically speaking, it's a dead space because there's no exchange of gases. All right, so for function, it's called anatomical dead space. Okay, and that is the conducting zone, as you can see here. I may think it's big, but trust me, it's way smaller than you think. And we'll get into the details of why it may seem bigger than it actually is. You know, you see the respiratory zone, you're like, oh, it's so minute in comparison to the conducting zone. No, that's not the case. We'll get into the beauty of it in a bit. So as you can see, the conducting zone, or quote unquote dead space, there's no gas exchange. All right, just bulk flow, just air coming in. Okay, and that it being called dead space doesn't mean it has no function. It has a function, but when it comes to exchange of gases, it's dead. So we call it dead space. Okay, while the respiratory zone, the gas exchange space, right, allows for gas exchange, right? The gas passively diffuses and no air currents. It's not like the conducting zone where just the air flows. Okay, we'll get into the details of that later on, but as you can see here, right, the respiratory tract divides 16 times for the conducting zone, right? And then another 7 times for the respiratory zone. As you can see here, from the 1st till the 16th division, it's called the dead space, conducting zone, just air flowing in. Okay, and just imagine the sheer amount of alveoli you'll get out of all these divisions, right? Just 2, 4, 6, 8, 2, 4, 8, 16, yeah, math. Right, so you can see the amount of alveoli I end up with, right? But for the first 16 divisions, there's no gas exchange. It's only 17, 18, 19, 20, 21, 22, 23. So the last 7. Okay, so it's 23 divisions in total, right? But only gas exchange in the last 7. Okay, so again, what's the difference between dead space and gas exchange space? Can somebody tell me that? You can type it in the chat or unmute.
Dead space is just for movement of air. Gas exchange space
Yes.
is where gas exchange happens.
Yep, no gas exchange in dead space. That is correct. Good. That's perfect. All right, so these are the details, right? Gas exchange region, this respiratory zone, right? From branching generation 17, including 17 and 23. Okay, and you can imagine the amount of alveoli and the just the surface area you'll get, right? Because of all these divisions, right? So you can see it has a surface area of 1 meter squared per kilogram body mass. So basically 70 to 90 square meters. It's just a huge area. It allows for better diffusion, right? So it's very thin. The membrane is very thin, right? As you guys saw in the in that picture. All right. So imagine the huge space with the thin layer of alveoli that allows for the exchange of gases, allows for a great diffusion, right? Somebody's unmuted the mic. Do you have a question, or is it
Yes.
by accident? Yeah.
Do we have to memorize, for an example, the body mass 70 to 90, these numbers? And like
Not precisely, no, but it's very simple to understand. It's just you have 1 meter squared for each kilogram of your body. Okay. I don't think you'll be questioned on it. Again, Dr. Shams, thank you for reminding me. Dr. Shams really just cares about you understanding the concept. He does not care about the details as much as the concept. He may bring details, obviously, but he really, really cares about the concept. And that showed in the SAQs. Okay. I remember when he taught us Reno, right? There was a gap of like 1 month, even more, of HLS that he didn't teach in. However, even the first lecture of Reno, he reminded us, and no, I want you guys to understand the question. Just understand. Because once you understand what Dr. Shams wants you to understand, the question will be a breeze. Okay? So these details you can keep in mind, sure. I'm no one to tell you whether he's going to bring it, definitely yes or no. But out of my experience, Dr. Shams really cares about you understanding the concept. Okay, did that answer your question?
yes, thank you.
Perfect. Again, as you can see here, along with that huge space and surface area, you get a very, very small thickness, as you can see here, right? Very, very, very slim. Again, allows for the diffusion of oxygen, right? And that thickness also changes from the first 16 divisions and the lower 7. Okay, so it shows it has a function. It's just that for gas exchange, the 7 and below divisions, the last 7 divisions, right, are where gas exchange occurs, okay? Again, so lung volume at FRC, put that in mind, FRC is approximately 3 liters, okay? Now, you may not be familiar with the terms, but I'll get to them in a bit. And then 2/3 of the tidal volume, which is the alveolar space during quiet breathing, okay? So you see all these terms, quiet breathing, tidal volume, FRC. We're gonna define them in a bit. But again, anatomical dead space, it extends from the airway opening to branching generation 16. Okay. And the dead space volume is around 0.5 liters. Okay. So there it is. Calculations. So what is tidal volume? What is FRC? Well, what are all these terminologies? Basically, FRC is called, stands for functional residual capacity. Okay. And then for tidal volume, it's basically the amount of air you don't fully breathe in or fully exhale, okay, normally. You see, the amount of air you breathe in normally, right, it's called the tidal volume. So it's not your whole lungs volume, right? It's just the amount of volume that you usually breathe every breath. Okay, so it's called tidal, as you can see, because I remember as tides. So it comes and goes, comes and goes, comes and goes. It can go up because you can breathe in so much, or it can go down as well. You can exhale so much, right? These details we're going to discuss in a bit. Right, just keep in mind that the functional residual capacity is 3 liters. Okay, is that clear? Is everything clear so far? Somebody type yes or no. Okay, perfect. Okay. طيب, anatomical and physiological dead space. That's why I took physiological away. I didn't mean to mean exactly this, all right? Because it can be confusing. Okay, so anatomical dead space is the normal region of the respiratory system where diffusion and gas exchange do not occur. Okay, they don't happen there, as we previously discussed. Only bulk flow movement of air from breathing in, just the conducting system. Okay, ventilation, just the air, the room has ventilation systems, obviously. Okay, now physiological dead space is different. Okay, gas exchange should occur there, but it doesn't. So that we call that physiological dead space. Okay, so it's when part of the alveoli, which is usually involved in gas exchange and diffusion, becomes either damaged, not perfused with blood, or collapsed. Right. So since now that space that should have been diffusing oxygen, right, is not functional due to a collapse, no blood. So where will the oxygen go? Or it may be damaged. So now it cannot go exchange anymore, and it becomes called, it becomes the dead space, okay? Anatomically speaking, it's not where the dead space is, but out of, physiologically speaking, right, it's termed the physiological dead space, all right? So the anatomical dead space, in addition to the alveolar dead space, are referred to collectively as the physiological dead space, all right? So anatomical dead space, the ones we've talked about before, they're the normal, everybody has anatomical dead space, right? But physiological dead space happens when the supposed area for diffusion, right, does not diffuse oxygen for whatever reason, okay? So this is called the physiological dead space. So physiological dead space is always equal to or more than the anatomical dead space. Is that clear? This may be confusing, so please, if you have any question. Okay, yes. I need to see another yes. Okay, perfect. So again, to recap, anatomical dead space is the upper side, the upper half, but the physiological dead space is the upper half, in addition to the space that you should have had diffusion happening to it, right? But for whatever reason, it doesn't have diffusion, okay? All right, so the functions of the dead space. Again, it's called dead because there's no exchange, okay? However, it has functions still, okay? So it conducts air to the gas exchange region of the lungs, obviously the tube system, okay? It warms the gas up to body temperature because you need it to be warm, obviously. Increases the humidity of the inspired gas, the saturation level at 37, that's the body's temperature. And it cleans the inspired gas and dust from other contaminations. You don't want just any air you breathe in, right? To reach the capillaries. It may damage them, right? And that's why you have certain protection systems, right? Whether it's cilia, goblet cells, and more, right? To help protect the alveolar space from being damaged or having any contamination happening to it, okay? So that's the function of the dead space, right? And so dead space volume and alveolar volume. The volume of our breath, the total volume, the normal breath, not our full breath, during normal breathing is about 500, right? That's right estimation. Right now, as you're sitting, you're breathing in and out 500. Now that I told you, probably changed, okay? From which 150 milliliters, right, of this 500 milliliter that you just inhaled, right, sits in the dead space. Okay, so again, this is the dead space. Excuse my, they call me Picasso, okay? And then it branches, okay? And then let's say here is the respiratory zone, right? So whatever was there, right? The dead space that we talked about, the anatomical dead space, is approximately 150, okay? As you can see here, let me show you, previous slide. Yep. Okay, up till here, you may think it's a lot, right? But there's a huge difference in surface area, okay? That's why the air that sits here, okay, out of is around 150 milliliters, okay, of the tidal volume, the volume you breathe in and out normally, okay? So again, the volume of our breath, tidal volume, during normal breathing is about 500. That's the tidal volume, in and out, normally, resting, okay? From which 150 remains in the dead space. And the other 2/3 reaches the alveolar space. Is that clear? I need to see a yes. Okay, perfect. So I hope everybody is okay. If you have any questions, feel free to ask me. I'll give you some time. It's a checkpoint. No questions? All right, perfect. Okay, so this is just the feeling of the, obviously you're gonna get into the details with the histology, anatomy, right? But the way Dr. Hashim likes to teach is that he likes to, I understand everything. Again, Dr. Hashim, understanding. Okay, so you get the bronchi, right? They're made of cartilage, so they're fairly rigid. Okay, they're strong. They need to be strong. They need to always be open. Okay, that's why the cartilage is there. Okay, you have smooth muscle, which can alter the diameter, right? You guys must have heard of bronchoconstriction, bronchodilation, just like vessels, right? You have the glands and cilia, right? This is the protection system. of it. The glands entrap any pathogens, and the cell to move it up. Okay, so it's protection and trapping molecules and glands as well, mucus, right? So you get into the details and the nitty-gritty of them and the histology, but it's just for your understanding. Okay, now you get to the bronchioles. Okay, they don't have any cartilage, they have a lot of smooth muscle, so you can assume there's a lot of constriction or dilation there. Okay, relaxation. They don't have any glands, and the cilia are only in the larger ones. So these details you'll know in the histology. Don't be too hasty with it. Okay, and then finally you have the alveoli. Okay, have type 1 cells lined up by the main thin membrane of alveolar epithelial type 1 cells. They're sustainable for gas exchange. They're the thin ones that we talked about. Okay, and you have macrophages. Okay, again, for immune reasons, right? You need to phagocytose any foreign bodies that your body doesn't need or doesn't want. Okay, again, keeps it clean from waste materials. Okay, I think it's this the histology, anatomy, no physiology here, so you gotta understand it. All right, so this again is the epithelium. As you can see here, cartilage, glands, no cartilage, no glands, a lot of smooth muscle. Okay, as you can see here, cilia starts to decrease. Okay, so it's only in the larger bronchioles, as we previously mentioned. Okay, again, details you're gonna know later, but just for information. And then you have the alveoli, totally different. Okay, and they're mainly like this for a physiological function, obviously for the diffusion. Right? It all makes sense. All right, so we're basically done with the first lecture. It was very quick. All right. Obviously, there are in Dr. Hashim's slides there were definitions of all of pulmonary physio. It's just basically what each term means, okay, or what each letter refers to. So it includes everything. You can go through them. Eventually, you'll learn them along the way, okay. But if he ever mentions something, and you're confused as to what that may mean, the letter or whatever, you can go back to the first slides of the first lecture. Okay, so again, we've discussed the properties of blood gas barrier and how it's ideal for passive diffusion. Its anatomy, the conducting and respiratory zones. We talked about these, bulk flow, and where gas exchange happens. Difference in gas movement in conducting and respiratory zones, bulk or diffusion. Okay, the anatomic dead space is the volume of the conducting airways, the 150 we've talked about. Okay, and the physiological dead space is greater than or equal to the anatomic dead space, right? And the reason for that is the dead space, the anatomic dead space is going to remain the same, but the physiological dead space may change due to lack of perfusion, occlusion, or just damage. Okay, so if the alveoli collapse, obviously they can't really diffuse air, so they're technically termed dead space. Is that clear? Is everybody good? Yalla, interactive guys. Yalla. Okay, good. Right, perfect. Okay.
Yes.
Tamam. Okay, so lung volumes, right? I love this diagram. It's $1 million diagram. All right, and just describes to you the different volumes of the lungs. It's just not in and out. It's not it. We have different divisions that we're going to talk about. You can see here a familiar term, tidal volume. Okay, it's a very small volume. Okay, you have the residual volume. Okay, so it's at the bottom. All right, the expiratory reserve volume and the inspiratory reserve volume. All right, so basically, right, the residual volume is the amount of air that you cannot breathe out. This air has to stay in the lungs no matter what. Because think about it, if you take all air out from the lungs will collapse, right? Pressure. Okay, so this volume must stay in the lungs. Okay, and it has a certain amount. We're going to talk about it later, right? Normally, you're not fully exhale to your limit. You don't just breathe upon the residual volume, right? The air you breathe, too many scrabbles. Okay, so the air you breathe in normally, right? I want you all right now to exhale it all out. Just exhale all the air you breathe in, right? Normally, not fully, not just on a normal level. Just exhale all of it out. okay? You're gonna be, you're gonna have a remainder of air, that is the residual volume. But whatever air you just breathe out to your max, it's called the expiratory reserve volume, right? It's the air you can exhale, but you don't, right? You're not usually like this. Whenever you're confused about questions regarding this topic, just breathe, just sit back and breathe, okay? You're gonna understand, it's very simple, okay? The tidal volume, right, is the waves, okay, that you usually breathe in, right? You can exhale, okay, to a certain point, right? Below that point is the volume that you cannot exhale, the residual volume. The volume you can exhale is called the expiratory reserve volume, ERV, okay? And, normally, right, we've talked about the FRC, keep it in mind, because we're gonna add these together and we're gonna turn them different stuff, okay? And so the tidal volume, the waves, and the maximum amount of volume you can breathe in. Now all of you breathe in. I hope you guys did that. Okay, that's called the inspiratory reserve volume, the volume you can breathe in fully, right? But you usually don't. Okay, so it's basically the capabilities of inhalation or exhalation. Okay, and usually the tidal volume is just that little wave in and out, in and out. That is sufficient for whatever you're doing right now. Right? Obviously, if you're doing more work, it changes. Okay, but these are the basics. Okay, and so as you can see here, end of normal expiration, that's the normal one. End of maximal expiration, maximal. Nothing goes beyond that because you need some air inside of the lungs else they'll collapse. Okay, and that's the end of normal inhalation or inspiration or maximal inspiration, as you can see here, right? So any questions? Is everything clear? Perfect. So how do we measure all these different volumes? Now it gets a bit tricky. You have to understand the concept, that's mainly, okay? But there's something called spirometry, okay? And it measures the tidal volume, again, the waves, okay? And inspiratory reserve volume, the maximum amount of air you can breathe in, right? And expiratory reserve volume. Now, if you notice, all these volumes are volumes you can change, okay? You can normally breathe, maximally inhale, or maximally exhale, right? So we connect a patient or whatever, a participant, to this device. I think it's called the spirometer, okay? And we connect the respiratory system, right? And you see how they close the nose here, so there's no leakage, okay? To a tube. And there's a valve here, okay? There's air. And there's water, and there's this complicated machinery that draws the differences of volumes you induce, right, on a graph. Okay, so as you can see here, let's just clear up all of this. Okay, this is the tidal volume. You can imagine this up and down changing and reflecting on the graph. Okay, that's due to the change of volume inside here. Okay, and then imagine the patient or the participant just fully exhaling. That'll create this reflection on the graph, the expiratory reserve volume, or maximally inhaling, changing the volume inside of here. It will create this reflection on the graph. So a spirometer, okay, is the volume you can change. You can change, okay? Change voluntarily, okay? You do that. But then some of you should have asked that, what about residual volume? How did we discover that? How do we get to know the amount of residual volume if we can never change it? We can't ever get it out of our lungs, right? Normally, okay? And that is through a method called inert gas dilution. So basically, inert gas dilution measures residual volume and functional residual capacity, FRC, right? And total lung capacity. Now, obviously, if you don't know the residual volume, you won't know the total lung capacity, okay? You have to know it if you know everything, okay? So the inert gas dilution method helps us measure the residual volume and the function of residual capacity. We're going to discuss what that is in a bit, okay? And then the total lung capacity. Obviously, if there's one missing capacity that you did not, or one missing volume you did not measure, you can't measure the total lung capacity, okay? And they do that by basically putting in helium, right? And a device, okay? The valve is closed right here, so there's a certain concentration that they measured of helium, okay? That's before the valve is open, okay? You don't know the lung volume yet, okay? You just know the volume here, okay, and the concentration of helium here, right? Now, you open the valve and breathe in, breathe out, breathe in, breathe out. Obviously, the concentration of helium changes, okay? And so that's after equilibration, right? Equilibration of the helium concentration, right, mixed with the lung volume, okay? Has a different concentration, and through that, they were able to measure the residual volume, because obviously the concentration will go all the way down to the residual volume, okay? And so as you can see here, the fraction dropped, indicating that there's the residual volume, okay? And this is all the calculations for them. They look also complicated, but again, Dr. Shams just mainly wants you to understand, okay? We opened the valve, we mixed, right, and we measured the concentration, okay? And we can indicate if the concentration is amongst a certain area, that the area or the concentration that was diluted equilibrates to this area, okay, of volume, this amount of volume, okay? I know it looks all scary, but it's just the concept of like, how did we measure this residual volume? And because we managed to measure the residual volume, we can now measure the functional residual capacity and the total lung capacity. Now, what is the functional lung capacity? Or sorry, functional residual capacity. Okay. Again, let's read through the math study. A sum of two or more lung volumes is defined as lung capacity. Okay. Lung capacities are listed below and illustrated in this summary figure of lung volumes and capacities. So you have the inspiratory capacity, the amount you can breathe in. So it's the total volume plus the inspiratory reserve volume, the maximum amount of air you can breathe in, right? And then air you breathe in normally, okay? Since you can breathe them in, that's called inspiratory capacity because two volumes added, okay? You have the functional residual capacity, sum of residual volume, the one we can't breathe out, and the expiratory reserve volume, okay? The maximum amount of air you can breathe out, okay? So air we can't breathe out and maximum amount of air we can breathe out, okay? There's a graph you guys will see in a bit. It'll help you better understand, all right? So again, capacity is the addition of two volume, right? So inspiratory capacity, as the name indicates, the amount of air you can breathe in, right? Functional residual capacity, right, is the residual volume plus the expiratory reserve volume, the one you maximally exhale, okay? So that and below, the expiratory reserve volume and below is the FRC, okay? And now, because we have just that residual volume, we calculated it through the inert gas dilution, we're now able to measure the functional residual capacity because it's the maximum amount of air you can breathe out plus the residual volume, right? We weren't able to get the residual volume in the spirometer, okay? Now we can get it through the inert gas dilution method. So it helped us obtain the residual volume and the functional residual capacity, right? Which is the addition of two volumes, okay? And because now we have everything, now we can measure the total lung capacity, okay? Is everything clear so far? All right, perfect. Okay, so again, vital capacity now, right, is the sum of expiratory reserve volume, total volume, and inspiratory reserve volume, right, which is the largest breath that can be taken. So basically, it's all that the spirometer can measure, okay? If you notice here, the expiratory reserve volume, you can fully breathe it out. Total volume, you breathe it normally. And the inspiratory reserve volume is whatever you can maximally inhale, okay? So that's the vital capacity. Basically, it's from the residual volume up, okay? Does that make sense? Back to this $1 million diagram, as you can see here. There's a better diagram I'll show you guys in a bit. Okay. But just to make sure you guys are clear on it. Okay, expiratory reserve volume plus tidal volume plus inspiratory reserve volume, right? So that is the vital capacity, addition of volumes, capacity. I cannot read, 1 second. So it's basically what we maximally inhale and exhale all together. Yes, anything except the residual volume. And you have the total lung capacity, okay, which is everything, basically. So the vital capacity, right, all three volumes, plus the residual volume, because vital capacity doesn't include residual volume, okay? Is everything clear?
Can you go to the graph for 1 second? The
This?
graph is, yes, this one. So
Yeah.
basically, expiratory reserve volume is the maximum expiration.
Yeah, the maximum amount of air you can breathe out.
So, okay, I'm kind of confused. Why does it say end of normal expiration in here? The arrow.
No, it doesn't. It doesn't say that to the expiratory reserve volume. It says that for the tidal volume.
Oh,
As you can see here,
okay.
maybe the scrabbles. Can you see that?
Yeah.
So that's expiratory reserve volume. Okay. And then this is the normal end of the normal expiration. Normal expiration. Okay.
Okay. And the
Does that
residual
make
volume
sense?
after, like, it's the volume after we maximally exhale, right?
Yeah, it's basically residue. We know residue, remnants. Okay. It's the air that remains in the lungs, right?
Yes.
You can't physically breathe that air out. You can't exhale it out. Okay. Else the lungs will collapse and the body doesn't is incapable of that, right? And it has a function. It gets renewed. It's not just some old air. It gets renewed. But that volume of air must remain in the lungs so the lungs don't collapse. You know, and it's just important for the integrity of the lungs, right? You just basically cannot breathe that amount of air out. Got it?
Yeah, I got it.
Okay. All right. Okay. So this is. If the other one was $1 million, this is $1 billion diagram. It shows everything here. Okay. The tidal volume, the waves, right? Normally, if you guys remember, only like the good memory people can remember that it was around 3, right? The functional residual capacity goes up to 3. That's normally, you know. The tidal volume is like 500, above 500, 500, 500. That's normal amount of, you know, volume of breath you take. Okay. Now, if you maximally inspire and inhale, okay, get the inspiratory reserve volume, right? And if you add that to the tidal volume, right? This is called the inspiratory capacity, right? So tidal volume plus inspiratory reserve volume gives you the inspiratory capacity. Okay. Now, for exhaling, the expiratory reserve volume, the maximum amount of air you can breathe out, okay, plus the residual volume, the amount of air you cannot change, it's just stuck in the lungs, right? Added together, they give us the functional residual capacity. Okay. Now, whatever we can change, right? So basically everything besides the residual volume is called vital lung capacity. And everything, including the residual lung volume, is called total lung capacity. Is that clear?
And exhaling reserve capacity is basically the expiratory reserve volume and the tibial volume, right? Which is the same as the inspiratory capacity.
You mean the functional residual capacity?
We have inspiratory capacity and I think expiratory capacity, or we don't have expiratory capacity.
I cannot hear you. Your voice is a bit muffled. Come again. Don't worry. Say it again.
The expiratory capacity, which is the maximum like we can expire, plus the
It's
what
not
is
called
it
the
called?
expiratory capacity. No.
Don't have.
Capacity indicates addition of volumes.
Uh-huh.
Okay. So there is no such thing as maximum expiratory capacity, right? Because maximum expiratory capacity, if you want to call it capacity, it's not capacity, is the expiratory reserve volume. It's the amount of air you can breathe out. Okay,
Okay. And plus
but I
total
get what you
volume,
mean.
or
Whatever
we
you
don't.
add, if you add the residual above the residual volume until the top of, but it doesn't work like that. You know, just memorize them as is right there. They all make sense. You know, residual remaining, expiratory reserve volume, the reserved amount of air you can breathe out. You don't usually breathe it out, but you can if you want to. Okay, and so this is the function of residual capacity, the air that remains, usually like not breathed in or out. That's the amount of air normally at rest remaining. Okay, the amount of air you breathe in normally resting is called the tidal volume. And respiratory reserve is reserved. It's kept so you can breathe it in if you want to. For example, you're running, you need more air. Obviously, you're going to use more of that reserve volume. Got it? And so you add these volumes together, tidal and respiratory, you get inspiratory capacity. Okay? Expiratory reserve volume, residual volume, you get functional residual capacity. Capacity indicating two volumes being added together. Again, vital capacity is anything you can change. So everything besides the residual volume. Okay, I'm talking volumes here, not the don't mix it with the functional residual capacity. Okay, as you can see, it includes this until here. Doesn't have anything to do with the functional residual capacity. Okay, and then total lung capacity is everything. Is that clear?
Yes, thank you.
Alhamdulillah, you're welcome. Okay, so checkpoint. Question 1. Now you guys can unmute and give me your answers. So I'll give you guys 10 seconds to read, and then I'll tell you to unmute. Okay. Yalla. Can you guys answer it for me? If you go on to unmute, even explain, that'll be good. Just I want you guys to be interactive, okay? We're here to learn. Okay, so we have A. All right. Any other answer? C, okay. So far we have A and C. Any other answer? I need to break even. Well, I want at least one more answer. Okay, another C. So 2 C's and then 1 A. All right. So the correct answer is indeed C. Okay. And we can just go back and just use the graph. Okay. So here, before we use the graph, what do you want? What do you need? The residual volume. Okay, how do we measure that? Right? Don't care about the 15 breaths per minute. What do you need with that? What benefit did that give me? Okay. Sure, total lung capacity. You may be like, oh, the total lung capacity, but it's not as useful as you may think it is. Tidal volume doesn't really play a role when measuring the residual volume because it's up. Okay. So you remain with FRC and expiratory reserve volume. Okay. If we go back, as you can see here, FRC is expiratory reserve volume, right? Plus residual volume. Okay. So now FRC equals ERV plus RV. Okay. Back to math now. If we want to measure for RV, just minus ERV, okay? Now, it may look like physics, it's not, don't worry. It's just basic mathematics, okay? It doesn't really have to do much with memorization here. It's just the concepts you need to understand, okay? So now FRC minus ERV equals RV, all right? And so that will be 3 liters, okay? Minus 1.5 gives us 1.5 liters, which again is like equivalent to milliliters. Okay, is that clear? Just multiply by 1000 خلاص. Perfect. Tamam. All right. Yeah, now for question 2. All right, so we have 2. Some people say 2. Some people say 3. Okay, we got another 2. Okay, any other answers? I'll give you guys more time to think. This must be an indication. You change your mind, okay? No, don't change your mind, no. All right, well, the correct answer is C. Okay. Yeah, as you can see by the graph here, this is the tidal volume. Okay, so below that tidal volume, all the way down, would be the functional residual capacity. Okay, and so that includes, right? This is the spirometer. Again, yes, spirogram. If you guys remember, the spirogram doesn't measure, it doesn't measure the residual volume. So the reflections seen on the spirogram, right, will not indicate residual volume. This is just the maximum point of exhalation, right? Which they determined later on that the residual volume would be 1, as you can see here. It did not reflect upon the spirogram. Okay, the spirometer wasn't able to detect it because it's incapable of measuring the residual volume. That's why the inert gas dilution method. Okay, but they gave you the hint of like the residual volume is 1 liter. Okay, so now you know this and below is residual volume. Okay, and up to the tidal volume, okay, is the ERV. Okay, so again, it's easy to calculate now. You just, that's what I did, just on the graph. Okay, add them together. خلاص. It's easy now. Okay, is it all clear? So you add from 3 till below, that's the FRC. Is it all clear? Clear. I want all 3 of you to say clear. All right, and
Yes,
I may
yes,
ask
thank
why.
you.
Okay, perfect. Perfect. Okay. Checkpoint 3, third question, yalla. All right, yalla. I want everybody to answer. So we have C. What else? Again, I'll give you guys a hint. Okay, we have another C. Okay, we have a B. Another C. Is that the MSA development? Okay. All right. Another B. Okay. Again, I'll give you one last hint. Okay. Everybody, I want you to re-answer. Okay, we're changing minds now. Good, good. It's the residual volume. Remember it, right? And spirometry. Okay. I just mentioned it. What does spirometry, right, not measure? What can it not measure? Exactly. All right. And so if it cannot measure RV, can it measure the FRC? It cannot measure the FRC, right? Exactly. So if RV isn't measured, okay, FRC isn't measured, then the total lung capacity cannot be measured as well. All you can see from the spirometer is the vital capacity, what you can reflect upon the spirogram. Isn't that right? And so again, what's the answer? Okay. Okay. Great, yes, it is B. Does everybody understand each question I asked? I'll pick a random ID to answer. I want to make sure. Okay, perfect. Right, because they're basic concepts. If you're too hasty with learning them, you forget them. You can get confused. Okay, perfect. More and more interaction. Okay, good. Perfect. All right, so please differentiate. They all build upon each other. Vital capacity, just the name capacity means addition of volumes. Okay. Expiratory reserve volume. Okay. Inspiratory reserve volume. They all indicate, right, what they mean. It's very simple, right? And you can try to also practice it, okay, with yourself. All right, so now effects of aging, right? So this graph, actually, I want one of you guys to explain this graph to me. It's very self-explanatory. So can one of you step up, please, and unmute to explain this graph? Yalla, guys, one. See age here, increasing. Yalla, bismillah. Does nobody want to step up and explain the graph? You guys, it's very self-explanatory. Age and lung volume. We know all these terms: vital capacity, total lung capacity, residual volume. We know all these terms. I just want one person of you guys to explain the graph. We're not ending the session until everybody understands.
I'll explain it. Oh, or someone
Okay,
else can.
perfect.
Oh, okay then. So basically what this graph is saying is that in the first year, 0 to 20, there is an increase in residual volume and also vital capacity. But after age 20, total lung capacity, it evens out to like a sort of like plateau. But as you get older, the residual volume increases, but the vital capacity decreases. And so
Great.
total lung capacity stays the same. It's just the vital
Mhm.
capacity and residual volume that change.
And what increases and what decreases?
The residual volume increases, but vital capacity decreases.
Perfect. And for a good reason, you know, the older you grow, okay, the weaker the muscles become, and, you know, the harder it is for the lungs to push all of this air out, right? So after a while, right, you get the plateau, okay, and then after 60, you become too weak to push all the air out, and so it gradually increases the residual volume. Okay, it's because you can't push that air out now because it stays in a stationary. It's called residual volume, right? It remains there, doesn't like that amount of volume, not the same air. The volume, right, is constant. Okay, and as our colleague here explained it very well, thank you so much. Yeah, so with age, residual volume increases, but the lung capacity stays constant. Okay, however, because the lung capacity stays constant, the residual volume changes, increasing. Okay, the vital capacity decreases. Because again, vital capacity, what is vital capacity, you guys? Yeah, I need answers.
It's basically the expiratory volume and inspiratory volume, and we also have the tidal volume, all three.
Exactly. Perfect. Yes. So basically anything you can control. All right. Okay. ERV. Okay. Perfect. Great. Okay. So reduced vital capacity. Okay. Whatever you can control. You get skeletal abnormalities. Okay. Kyphosis. Kyph scoliosis. Sorry. You get weak respiratory muscles. That also may happen in aging as well, right? But pathologically speaking, myopathies, poliomyelitis that also affect, right? Myasthenia gravis or lung disease. Okay. The lungs themselves, the volume inside of them changes. Okay. So you get fibrosis, collapsed lungs, pulmonary edema. All these change the volume inside of the lungs, and therefore they pathologically, if they were to be pathological, decrease the vital capacity. Or you can get obstruction as well, changing the vital capacity, the amount of air you can breathe in and out. Okay, so is it clear how all these different pathologies can affect vital capacity? Yes, yes. Okay, perfect. Great.
Yeah, thank you.
Come again, please. I'm assuming you said yes. The mic was a bit laggy. But if you have any questions, please ask me. Okay. Now, changes in lung volumes in diseases. Okay. So obstructive lung disease. What can you indicate from that name? Okay. That the lungs are being destroyed. Okay. And so that would reflect with a higher lung capacity, right? But a much higher residual volume. Okay. And so that is obviously pathological, because now the ratio of residual volume to total lung capacity increases. Okay. And the reason for that is once you destroy the alveoli, right, you have more space. Okay. But the alveoli are also important in pushing the air out. Okay. You'll understand more of the details of how they push that. But just for now, right, it's like an elastic band. Okay. They push them out. They help with pushing the air out as well. Okay. So if they're destroyed, the spaces that are left by these alveoli increase, right? So increasing the total lung capacity, but ever so slightly, and especially in comparison to residual volume, the amount of air you cannot push out anymore, right? Because the morphology of the alveoli helps with, also aids in pushing the air out. You're gonna know the details of it later on, okay? But for now, just know the alveoli and the alveolar sacs also push the air out. So if they're destroyed, less air can be pushed out, right? Increasing the capacity, okay? Because now more space is empty for the air to be in instead of the alveoli, right? However, less air can be pushed out. And that happens in emphysema, for example, right? Just in general, obstructive lung disease, destroying the alveoli. All right, so does it make sense? All right, yes, I need another yes or a no. I'll be more than happy to explain. Yes, okay. All right, now restrictive lung disease. What you can indicate from that name is that it restricts the lungs, right? And so that reflects with decreased total lung capacity, decreased residual volume. However, on the same level, there's like relatively the same. So the ratio doesn't change. Okay. However, it's still pathological. Okay. The ratio doesn't change because the total lung capacity decreased, right? But the residual volume also increased. So everything in restrictive lung disease decreases, sorry. Okay. Everything in restrictive lung disease decreases with the same ratio, unlike the obstructive lung disease, right? So because they're same ratio, okay, it doesn't change in restrictive lung disease. However, the total lung capacity decreases, okay, and the residual volume also decreases. Okay, is that clear, everybody? I need to see yeses. Okay, yes, yes, yes. Okay. All right, last question. Yalla. Okay, we have one F. Okay, one E, and I saw a C. See a lot of Spread, okay, another E. I need more answers, you guys. Okay, another F. Okay. Right. I'll explain it again, right? These are the scores for now. 1C, 2E, and 2F. Okay, I'll explain it again. And I'd like to see a change. Okay, so, and don't worry, guys, I got confused by it as well, Adi. Okay, so obstructive lung disease, the alveolar sacs themselves are getting destroyed, whether that be smoking, because of smoking, whatever it is. So emphysema, for example, is one of these obstructive lung diseases. Okay, and so when you destroy these sacs, okay, okay, you're emptying out more space. All right, I'll explain it in a bit, right? You're emptying out more space, okay, but due to the nature of the alveolar sacs, right, that helps in pushing the residual volume, right? You'll get more residual volume when you take out these alveolar sacs, okay? So yeah, sure, it gave us more space, okay? However, you can't push that air out. The amount of air you can push out decreases, right? Thus increasing the residual volume, okay? All right, so because relatively speaking, right, the residual volume and the total lung capacity, right, don't change equally, okay, you get an increase in the ratio. When the ratio increases, okay, you know it's obstructive lung disease, okay, it's damaging the alveoli, okay, and that is by a doubled increase relative to just a normal increase in residual volume compared to total lung capacity, okay. However, in restrictive lung disease or constrictive, whatever, okay, like pulmonary fibrosis, you guys know what pulmonary fibrosis is, right? So the lung capacity decreases, and so does the residual volume, okay? And because of that, they decrease equally, respectively speaking, right? So the ratio is normal, but it's still a pathological condition, okay? So I hope it's clear now, okay? So now I need to see the answers here. What do you guys think it is now? Yes. Yes, they do mean the same thing, yes. I took that question from Guyton, so I just need you guys to understand. And understanding is the main point here, okay? Okay, we got one F, and I saw two E's. Another F. Okay. I see why you guys are confused, okay? And the correct answer, drum roll please, is F, okay? That is because the total lung capacity is decreased, we get that, right? The residual volume decreased. But here, don't be very, like, think outside of the box. Don't be very monotonous the way you think, because maximum expiratory flow isn't the same as the ratio, right? It's the amount of air you can expire, right? And as we said, everything decreases in constrictive lung disease, right? And so that causes for a decreased ERV, right? Lesser amount of air you can push out, right? The flow is less, okay? So technically everything should be reduced. Is that clear for everybody?
Yeah, repeat it again, please.
All right. And so do you understand why the total lung capacity is reduced?
Yes, the problem is in the maximum expiratory flow.
Okay. Break it down. حبة حبة, okay? شوية شوية. Okay? Maximum expiratory flow. The flow of air that is expired. Got it?
Okay.
Okay. So when you decrease the total lung capacity, and as we previously mentioned, also decrease everything, equally. ERV, tidal volume, and just everything in general. Okay, everything decreases. Okay, the flow
Okay.
of air you can expire outside of your lungs obviously decreases. They didn't mention anything about ratio here.
Oh, okay.
That's what you guys
Yeah.
need to understand.
Mm.
Got it?
Yes, yes.
Is it clear?
Yeah, yeah. Thank you so much.
Perfect. So, key points to leave with. Okay, which lung volumes cannot be measured with spirometry and therefore are measured with helium dilation. All right. So, what are the volumes that cannot be measured with spirometry?
The residual volume and the
Vital.
no, the vital
Sorry.
right. Residual volume and the total lung capacity and FRC.
Right. Okay. So yes, FRC, residual volume, and again, if you can't measure any one of the volumes, any of the volumes, you can't measure the total lung capacity. Okay. And so, what does helium dilution method help us to measure? The helium dilution method, you guys. RV, yes. RV, what else? What is part of RV? Total lung capacity as well, yes. And FRC, yes, perfect. Okay. And so what does restrictive lung disease cause to how does it change total lung capacity, residual volume, right? And the ratio. Yes, so restrictive. Let's talk about restrictive for now. Right, restrictive, right? Obstructive. Right, yeah, yes, exactly. For restrictive, everything decreases. Correct. Right, the ratio stays the same. Exactly, yes. Right? But for obstructive, how does it change now, you guys? Yes, it increases it. Okay, everything increases. Okay, but what increases more? Ratio increases, yes. RV, yes, perfect. Perfect. Good. So just to make sure you guys understood everything, okay? I want to make sure you guys understood everything. Okay, let me go to the first question. All right. Do you guys understand why it's C?
Yes, but can I ask you a question?
Yes, of course.
If we could, for an example, use the residual volume and then we subtract it from the
I cannot hear
vital
you clearly.
volume, will that also help the
Unfortunately, brother, I cannot hear you properly. So if you can contact me and ask me the question. You guys have my number here. Okay. It's a very weird university. Okay. You have my number here. Please contact me. Okay. Or email me if you want. I don't mind. Okay. So the majority, you guys all understand the first question, right?
Yes, but I have two questions, okay, if you don't mind.
Of course. No, please.
Okay, in the residual volume here, they didn't give us the inspiratory capacity. That's why we couldn't like add them all together and then subtracting it from the total, right?
Yeah, there's no reason to measure the inspiratory capacity or the vital capacity when you can just shortcut it by measuring, by just subtracting FRC from ERV, which he gave you, right? There's no reason to use
Yeah.
tidal volume, right? Because if you remember this graph, okay, where was the graph? Yeah, okay. Functional residual capacity equals ERV plus RV, okay? You already know functional residual capacity is expiratory residual reserve volume, right? And residual volume, okay? That's the functional capacity. So if you have two mathematics, you can just calculate residual volume, okay? Because if the FRC is everything right? That you can exhale and not exhale everything below, okay? Then if you just know one other figure, you can calculate the residual volume. Is that clear?
Yeah, it's clear. And
Okay.
can you go like to the third question or like the fourth question? I'm not quite sure.
Yes, yes. In a bit, but I just want to make sure everybody understands the second question. Do you guys all understand this question, why it's 3? I don't want you to just say yes for no reason. Yes, doctor, please call me Aghiad. But thank you, though. All right. Perfect. Again, can a spirometer measure the residual volume? Okay, good, good. All right. And so what is reflected here, is it inclusive of residual volume, whatever this spirogram reflects? Exactly, it's not inclusive. All they told you here is that they somehow, right, they measured the residual volume and they just shifted the graph upwards 1 liter, as you can see here, right? So you can use that to your advantage, right? By just looking at the graph and finding the answer. Is that clear for everybody now? Perfect. Okay, good, good. All right. For the third question, brother, you can also ask your question now.
Oh, not this question then. It's the last question, I guess.
Okay, we're gonna get to it in a bit. Does everybody understand this question? Please, I'm giving you a chance. Don't worry, it's a very short lecture, Aslan. Yes, okay. And what was it, you guys? Answer the question again. What was it? If it's yes. If I see one wrong answer, I'll redo the whole session. Yes, yes. Who wrote C? Whoever wrote C, please contact me. Okay. Yes, it is B. Correct. Correct. Okay. Because again, spirometry. You cannot calculate RV unless you can't calculate FRC, unless you can't calculate total lung capacity. I hope it's clear. And whoever answered it wrong, please don't hesitate to contact me. Okay. Right. I hope everybody understands these. Okay. And this is the fourth question. Any questions regarding the fourth question? No questions regarding the fourth one?
Yes, I do.
Yeah, tell me.
It's not really a question, but like the reason why the maximum flow, because the airway resistance increases, right?
Yeah, you can also see it as that.
Okay, that's basically it.
Is everything clear now?
Yep.
All right, perfect. If you guys have any questions, please unmute, email me, text me, call me. You can also unmute right now, please. Right? You'll help other people. Perfect. I'm very glad it's crystal clear. And please, you guys, understanding is very important in pulmonary physio. Okay, especially Dr. Hashim. Right? I remember I didn't give it all that much time when it came to revision. However, because I understood the concepts properly, they stuck with me, and I managed to do very good, alhamdulillah. And again, if any of the concepts are unclear, right? Any of the concepts are unclear, please contact me. All right. I hope the session was good. Apologies for the lighting, and yeah. See you soon, inshallah. Salam alaikum.